Binomial distribution. Bernoulli trials and the binomial distribution. Suppose we have an experiment with two possible outcomes. For convenience, we'll call these a success, or an S, or a failure, F. And let's suppose that on each of the trials of that experiment, the probability of a success is little p. This is an experiment which will repeat over and over again, and each repetition is called a trial of the experiment. A sequence of such trials, when they're independent of one another, are referred to as Bernoulli trials. When I toss a coin repeatedly, and I refer to heads as a success, then that's an example of Bernoulli trials, provided the tosses of the coin are independent of one another. In such an example, we often count the number of successes in a fixed number, little n, trials. So that random variable x is the number of successes. For the binomial distribution, we'll require that the probability of success be constant over the n trials. So the probability the coin comes up heads is the same on the 13th trial as it is on the second, and that the n trials must be independent of one another. The fact that the third trial came up with a heads didn't affect the fourth toss. The binomial distribution. The probability function of a random variable x, which has a binomial distribution, is given by f of x equals n choose x, p to the power x, 1 minus p to the power n minus x. And the possible values of x, the possible number of successes in n trials, is any integer between 0 and little n, the number of trials. This is quite easy to show. Let's suppose we look at a given sequence, a particular sequence which has exactly x successes and n minus x failures. For example, let's suppose the first little x trials result in successes, and the last n minus x trials result entirely in failures. What's the probability of such a sequence? It's the probability we got success on the first trial, success on the second, success on the third. In fact, little x successes in a row, p to the x, multiplied by the probability that the last n minus x trials consist of failures, 1 minus p to the n minus x. That's the probability of one sequence which has x successes. How many such sequences are there? It's the number of ways we can permute these n symbols, of which x are s's and n minus x are f's. Or the number of ways I can choose positions out of the n available positions to place the s's in. In other words, it's little n choose x. So the probability of little x successes is n choose x times the probability of success raised to the power the number of successes, the probability of failure raised to the power the number of failures. Of course, we should also check that f of x is a genuine probability function. They're obviously non-negative values, but do they add to 1? To this end, we require the binomial theorem, which says that when you add n choose x, a to the x, b to the n minus x, over all x from 0 up to n, you obtain the expansion of a plus b raised to the power n. To use this in this case, we'll set a equals p and b equals 1 minus p. And then the sum of n choose x, p to the x, 1 minus p to the n minus x, is p plus 1 minus p, all raised to the power n. This is just 1 to the power n, or 1. Example. Suppose a statistics quiz has 10 questions on it. Each question has 4 possible choices. The student, unencumbered by knowledge, decides to guess each of the questions. What's the probability that the student guesses correctly 6 of the 10 questions? In this case, the probability of success on one trial is the probability of getting a correct answer, which is 1/4. And there are 10 questions or trials in total. Since we're guessing purely at random, we can apply the binomial distribution. The random variable of interest, capital X, is the number of questions that were answered correctly. And we're interested in the probability x equals 6. Well, that's n choose little x, or in this case 10 choose 6, times p, 1/4 to the power 6, times 1 minus p, that's 3/4, to the power 4, which works out numerically to about 0.016. I think the moral of the story in this case is that guessing isn't an ideal strategy. The binomial and the hypergeometric distributions are quite similar to one another. For both, There are two types of outcomes on every trial, either a success or a failure. In the case of a hypergeometric, we call the success, say, a type 1 item as opposed to a type 2. So both count the number of successes in a sample of size little n. The main difference is that the binomial distribution requires independent trials. When you're drawing from a finite population, you have independent trials if you draw with replacement after each draw. The hypergeometric, on the other hand, requires that the draw is being made from a collection of objects without replacement after each draw. This means that if the total number of objects for the hypergeometric capital N is very, very large, and the sample size is relatively small, for example, we're selecting telephone numbers in an employment survey from a population of 20 million, but we're only selecting little n equals 1,000, then there's very little difference in the population whether we replace after each draw or not. The composition of the population will remain much the same. And this implies that in that case, the binomial and the hypergeometric will be very close to one another. If the population is large and the sample size relative to the population size is relatively small, then we can use a binomial to approximate the hypergeometric. Here's an example. Suppose we harvest 300 items of fruit, 120 of them apples, and the rest 180 oranges. We've randomly selected 10 of these for a fruit basket. What's the probability of exactly 3 apples in the basket? If we use the hypergeometric distribution, sampling, in other words, without replacement, which would be the normal method of sampling, we obtain 120 choose 3 times 180 choose 7 divided by 300 choose 10. And numerically, that turns out to be 0.217. On the other hand, let's imagine that I did replace after each draw and use the binomial as a result. Then we obtain 10 choose 3, 120 over 300 to the power 3, 180 over 300 to the power 7, which is 0.215. So in this case, the population of 300 and the sample of size 10 was such that the binomial approximation to the hypergeometric is quite close. Here's review question 1. 100,000 lottery tickets are sold. 25% of the tickets win some sort of prize. Overwhelmed by optimism, you purchase 10 tickets in total, thinking to yourself that you probably have 4 winning tickets. What's the probability that you have no more than 2 winning tickets? That is, either 0 or 1 or 2. Pause for a moment and work out this. Proceed when you're ready to check your solution. Solution. The probability that each ticket wins a prize is p equals 0.25, 1/4. Since a large number of tickets are sold, the events that the first ticket wins a prize, the second ticket wins a prize, and so on, are approximately independent, Bernoulli trials. They're independent because there are so many winning tickets that you're not really depleting them as you run through your 10 trials. This is the binomial approximation to a hypergeometric distribution. So x, the number of winning tickets among the 10 we purchased, has approximately a binomial distribution with parameters n equals 10, p equals 0.25. And the probability that there are no more than 2 winning tickets among our 10 is the probability that x is less than or equal to 2. If we use the binomial probability function, this becomes 10 choose 0, p to the 0, 1 minus p to the 10, plus 10 choose 1, p to the 1, 1 minus p to the 9, plus 10 choose 2, p squared, 1 minus p to the 8. And replacing p by 0.25 and 1 minus p by 0.75, and calculating this numerically, we get an answer of somewhere around 52%. Indeed, we are quite likely to have 2 or fewer winning tickets in our batch of 10. Review question 2. Suppose there are 200 AXI students and 100 statistics students in a given class. 5 students are selected at random to form a committee. Given that there's at least 1 AXI student on the committee, what's the probability that exactly 3 statistics students are selected? Again, continue only when you've worked the solution out for yourself. Solution. Let x be the number of statistics students that were selected. X has a hypergeometric distribution. The probability function, the probability that x equals little x, is 100 choose x, because there are 100 statistics students in the class, times 200 choose 5 minus x. That's the number of ways we can choose 5 minus x xi students, divided by 300 choose 5. The question asks for the probability of exactly 3 statistics students given that there is at least one xi student. That's the probability that x equals 3, given the event that x is less than or equal to 4. The number of statistics students is less than or equal to 4 if the number of xi students is at least 1. Using the form for conditional probability, this is the probability x equals 3 and x is less than or equal to 4, divided by the probability x is less than or equal to 4. Of course, the numerator can be simplified to the probability x equals 3, and the denominator is probably most easily calculated by writing it as 1 minus the probability x equals 5. And if I replace each of these by the form for the hypergeometric probability function listed above, and evaluate this quantity numerically, it turns out to be something around 0.165.